Okay, so I hope you can see the screen, right?
Yes, sir.
Well, I will go by the slides I will put up because it's a little bit of pictorial, so I do not go by writing much in the first part. Later part, when we look for the roadmaps, I will try to write in more details. So when we call that something to be interpretable and explainable, we mean that usually, see, when we gradually form different parameters to learn and keep on improving the number of parameters in a way to make our learning prediction more accurate, where the primary point where we missed and gradually get more distant is the explainability or the interpretability factor, meaning that someday, nowadays, with the deep neural nets and all other kinds of very basic, from basic towards the complicated architectures that you result in and call as a model which is suitable to predict, which is suitable to interpolate wherever you want to use it. The problem is of these models is that they are very less explainable to the person or to the application where it is being used. I mean, suppose you are using a radiology images and trying to detect cancer, and suppose your model tells that it's a cancer because your lambda value is zero point 0.5. I mean, the patient, doctor, nobody will be very much satisfactory by that answer, right? And also, if a robot tells that I just landed on Mars because I can see that this epsilon value is more than zero point 0.5 and my mu value is less than zero point 0.6, so I landed here. I mean, it's not worthy to use it because you cannot explain on these decisions. So you build an autonomous car that got an accident, but you could not explain why the accident happened. It would not be helpful. So the present day of research potentially diverted from the model, technique, theoretical guarantees, all these we have studied in the course, towards how can we make our model more explainable or interpretable in that sense. So I will share with you one of the open source presentations that DARPA made when they tried to uh, first coin the term which is called an XAI, which is explainable AI. It's coined by David Gunning from DARPA. So with gradually when we moved from AI to ML to DL, what happened is that our machines becomes much more accurate in prediction. And as we can see, this Watson is a quiz model that can perform equally or even better than, I mean, very famous quiz masters. So it owned the quiz competition, and you know the story of AlphaGo. And as I have suggested you to look into the documentary movie, which is there in YouTube as well by DeepMind. So AlphaGo is a reinforcement learning based solution to beat Go players in the Go games, and it's a learning agent which plays with you and gradually learns the moves and ultimately beats the 9 Dan players like Lee Sedol and all. Also, these kinds of technologies are used in warforts and other sensor operations where the robot guides a particular troop of uh, the police or the border forces to navigate there, collects informations and give it. But on the flip side of it, you see that whatever it does, if something goes wrong, and even if something goes drastically very well, I mean, you need to know why I should trust the result, why it made a correct prediction. In case of failure, I must know that where the thing went wrong. So with that concept, which we lack in present models due to we somehow lacks in deep neural networks, all this, we only know the parametric values. A body of research has emerged to find that what is the interim things that a model is looking for to make a decision. So with that, what happened is usually when we do this machine learning course until I mean recent past, what happened is that we have a learning process which can, let's say, see an image of cat and can detect it's a cat with a higher probability. Now in the present day research over the last 4, 5, or let's say 6 years, it has happened that your learning process will automatically not just give you a value or a parametric estimations of something to be of some object or some outcome you wished, but it also give a prediction of why that outcome you want has been made by the model. So it also brings into two things in the flow. Earlier, we have a training data, we have a learning algorithm. As you know, if you know for the supervised learning diagram, if you remember, that the learning algorithm produces an outcome model which can predict well. Now, with that, we try to incorporate something called an explainable model as a top up and as an explainable interface, because not only you should have a model, but you could have mechanisms to query that model so that you could get what it is happening inside. And then we are happy with all the proceedings that we are getting is actually perfectly being done. So with that, if you look at the landscape that whatever we covered, also see the methods now is more familiar to you. We have covered many methods like Bayesian belief nets, deep learning, neural nets, ensemble methods, decision trees, some statistical methods, SVMs. Okay, some of the new terminologies are here. I mean, machine learning is a vast topic, so we could not cover all. This AOG means and or graph. It is much more explainable model. SRL is this statistical relational learning. CRF is conditional random fields, hybrid Bayesian networks, and MLN is, I think, Markov learning networks. So there are three parts primarily we do it. One is the neural network side, one is the statistical side, or extended version of it, we call it graphical model. And the other is the decision trees, which are mostly interpretable, so as all the models we have learned. And we can ensemble, I mean, this is shown as an ensemble of the decision tree with the graphical model. We can ensemble many things. So typically the explainability, if we try to plot in terms of a metric, though synthetic, but if we try to plot what is the prediction accuracy versus explainability, I think it is more or less now understood by you that decision tree is much more explainable than the neural networks, because decision tree, you can see that why it is taking a decision, because it has an if then else structure. So it is more explainable. Whereas neural networks is just a parametric learning. So it has higher accuracy because you can go deeper. As you know, nowadays you can sense every image, every object. You can just tell from an image through the recurrent neural network what is that image about. A baseball is being thrown by a player, as I saw in the last few classes. So prediction is very much good. Whatever you want, you can achieve, but the explainability why it is doing so, it's a questionable area. So the quest of recent days is that can we push this barrier where we have getting prediction accuracy to a higher level, also explainability to certain acceptable margin. So with that, there are many methods that people try to survey. One of the thing is that they try to find the explanation from the hidden nodes in the neural network, where the hidden nodes, can they tell us some information about what they are looking while they are composing the previous layer data and forwarding it to the next layer, which means we are trying to target here this explainability to increase a little bit. So one of the popular methods that has been followed is through visual question answering. I mean, one of the first papers came up in 2014 where it trains with an image with a little bit of pre-trained what is being in the image. Suppose you are pre-trained with the left side images, where it says that if you are exchanging a ring, it must be a wedding. It must be a wedding event. So if there is a bride, there is a groom, and there is someone who is officiating the event, it must be a wedding event. This kind of some training happened, and then finally what they try to do in this paper is they try to associate semantic associations. They try to learn in between that for a cat, if they try to recognize which part of it is trying to find this ears, the furs, the claws of a cat, and thereby determining something to be cat, and how this network forwards the probability of claws into the cats as an outcome. So this is one of the previous approach. We train it with some supervised set of what is happening. If we try to match that, we try to figure out from intermediate nodes some associations out of it. Also, people have in the era of deep learning, as you can easily understand, that generating caption from images is also a kind of explainability measures that we can provide. Suppose you look into this image and predict something. Plus, I also give you some explanation. There are vegetable fruits in the market. Some person is selling, a group of people is selling, a group of people is shopping in the market. That gives you a much better description why you categorize this image as a marketplace, right? So this is not very difficult, because you know now that CNN can identify object, and you know RNN can generate text of the descriptions from the object, right? So this approach has been done in 2016 paper, which generates visual explanations just by having a concatenation of a CNN structure with an RNN structure, where the RNN in particular uses LSTM, because as I have motivated you, LSTM sometimes is needed to remember some information from the past and to forget certain information in order to generate a meaningful caption. So this is one of the explanations that people try to generate from visual data, and they are quite successful in generating what is happening inside. The other kind of work, this is through the deep explanation generation in terms of either visual models or by pre-trained models. The other kind of thing people do, they try to introduce another model on top of it. I mean, suppose you learn a model, I will also give another model as an auxiliary model, whatever you learn with it, so that you could question the auxiliary model and get the interpretable answers. This auxiliary model often sometimes be an AND OR graph. It may be a hybrid Bayesian net where the probability value as well as the path can dictate you about the decision you are making. So 1-2 approaches I will summarize of this, that people sometimes use a GAN kind of a thing to generate the possibilities. So, I mean, you may think that suppose you have a set of characters as a training data, I mean, in your native language, and suppose you are trying to train something. So what you do is that here you generate from the subparts, you keep on generating different orientations, different variations of the data. Now what will happen is that whatever be the way you write, such generative model will aid you and dictate. So if you look at a chunk of these paths, particularly this chunk of this graph, it will dictate why I categorize this as the particular letter in your native language. Because I have seen that there is in the boundary, I got this kind of a curve, I got this kind of a curve. So it resembles like that particular letter. So you have a seed model, which is the correct, or I would say the oriented alphabet. From there, you generate certain different variations of it. You know how to generate it, right? Autoencoders, adversarial GANs, where you can just perturb a little bit on your latent model and can generate new images. We have seen all that, deep fakes and all. But suddenly, this kind of thing associated with whatever you learn can help you, that why you see that this character is a B. Why you tell this character is a B? Somebody could write it in a straightforward, somebody could write it in a curly way. But you have seen it by looking this. It has 2 loops, so I found it as a B. So this also can give you a little bit more explanation. And they call this as a concept learning through probabilistic programming induction. And this is a very famous paper because they try to imbibe human understanding of concepts using this kind of a model. That's why you can see this paper has been published in Science. So human level concept learning through probabilistic program generation. So this is one of the way people try to look at the interpretable models to use it to explain certain outcomes. One of the extension or rather the generalization of whatever we have seen is the AND OR graphs. I mean, they are not only a particular structure we do from a probability model, but we take an AND OR graphs to make a decision and object representation. And why this AND OR helps, if you see that what will be your AND nodes. Suppose you are trying to identify a rooster. Your AND node will be that whether the rooster's head looks like something which resembles a rooster, and its tail resembles a rooster, and its feet resembles a rooster. Now, what will be my OR nodes? Its head could be at 90-degree tilted, or its head could be same orientation, or its head could be 180-degree tilted. So these are OR nodes. How your head positions will matter. Now, again, so you can see here, I am seeing the subparts of the rooster. Then deep down, I am seeing only head and focusing it. So I am gradually focusing when I go deep down to the AND OR graph. I am gradually focusing a part of it and trying to dig down what are the saline characteristics in terms of variations as in composition of OR node and in terms of possibilities which I compose in AND node. And thereby, if I supplement this auxiliary model along with your model of prediction, then when you predict something, you traverse some path and you will say this head is 90-degree rotated, but it has a red mark in it and this, that, finally you get a decision. So at the bottommost layer, you will have some sketches, some textures, boundaries. Then a little above that, you compose decompose that boundary to make a face-like structure, a ear-like structure, an eye-like structure. Then you come up again, then you find the face, the tails and all that. And gradually this model helps you by going through a path along with the decision making you made, by going through a path to explain why that decision has been done. And it's a very popular model. It combines a little bit of generative and discriminative techniques. So it has been published in PAMI, which is one of the top tier conference in 2013. It says learning and or templates for object recognition and detection. So with that, we can also have a supplementary interpretable models along with it, not only directly putting inside our original prediction model the deep explanation. That is the first part that I mentioned. The third thing is that sometimes your model will also come as a black box, and then it is called model induction. It's a technique to infer an explainable model from your black box. So you do not know what the parametric values has been set. You can only see it as a black box, your model. You can give input, it predicts some output, but during experimentation, can you find out or infer certain explainability out of what it predicts? So there are many approaches right now going with it. One of the first famous approach was LIME. What does it do? See, it tries to give new images. And suppose this red region is the plus region and the green region is the minus region. See, I do not know how do I categorize in the model because model came to me as a black box. I can only experiment with it with an image. Now, the near boundaries that it finds with the probability of, higher probability, it tries to say which is the plus one and which is the minus one. How does it do that? Let's say it gets an image of this and I want to figure out what kind of guitar is it. Now you can see there are 2-3 approaches that will immediately follow from this, though this paper doesn't mention those, but the other papers which cites it mentioned. One is a saliency guided thing, that I can see that the saliency maps from which the decision is being made. For that, the black box model, I need to a little bit sacrifice. I need to know the saliency, how it is looking into it. And you can see the way it looks into the probability value is dictated by that. Excuse me?
What is saliency map?
Yeah, saliency map is that when you look at an image, which are the positions is more relevant to come up with your decision. Okay, so when you look at this image, if you want to see that there is a guitar in the image, so obviously the face of this in this particular image is not will be in your saliency map, right? Because you will to find out whether there is a guitar in this image or not, your saliency map will mostly govern towards the positioning of the guitar.
Yes.
Okay. So that's why this LIME is one of the first approach that it starts with a black box models. It arbitrarily try to predict a boundary and try to give confidences of positive and negative sample points. And the far away the points is, it gives less confidence about whether the positive thing is actually properly classified or not. But this has been extended to a multiple facets, often sacrificing the black box model to a white box model and also often extending it to SP LIME and all that. But this is one of the pioneer paper on the black box model side that we find. There has been ramifications of this model inductions in different kind of psychological or cognitive science areas as well, because sometimes depending on how a person is drawing or behaving certain things, it dictates some cognitive impairment as well. So if I have a model for detecting such kind of a cognitive impaired or some disease, then obviously I can use which portion of it or which is the boundary line where I can be highly confident that they have a cognitive impairment and some person do not have a cognitive impairment. And this paper again just extends the LIME approach to and apply it in terms of medical and cognitive psychological domains. And so that explainability, whether a person has cognitive impairment, I can also get it by looking at how a model can see whatever you are doing. So moving on, you can see this is one kind of an approach we do, but I have something more to tell here. Looking at the way I can figure out an electric guitar and acoustic guitar also click some other things in our mind, that sometimes occluding a part of a model, I mean, not representing or just hiding a part of a model, also can dictate which part of the model is more significant. Okay, so sometimes what people do, they just try to hide a portion of an image and try to see whether the outcome is dictated similarly even if we hide it. Suppose I'm trying to identify guitar. If I hide the face, the outcome will not matter. But if I hide this string, the outcome may matter, because if without this string, you could not figure out this thing is a guitar or not, right? So that dictates that which part of the neural network, suppose you are doing it in a neural network by neural network techniques, which part of the neural network is primarily sensing which part to make a decision. So people have experimented all this, and there are papers like GradCams, which often exploits the saliency guided map, such kind of occlusion, sometimes blurring the image a little bit, seeing whether the blur part doesn't matter, changing the foreground backgrounds, does it matter? So all these approaches comes under the same umbrella. Finally, in the explainable model parts, as we have seen that we incorporate some of the explanation within the model, we provide an additional model to provide explanation, and we query the black box, and sometimes we can infer certain decision making, and a little bit advanced techniques we have, as we discussed, but not in the slides, that saliency guided techniques we can use. But of similar importance will be of the explanation interface as well, because not only you supply a model or you equip the model to make some analysis for you, but how you represent that analysis succinctly to the user who is using it, so that he could refine it or he could refine his decision making and all is of very importance. And this is primarily more important when you go into a safety critical domain in devices, or in case of medical domain, psychological domain, because suppose some robot has learned, a learning agent is trying to dictate a doctor about or help out a doctor about an operation. Now, obviously, that agent should mention in such a way that is interpretable. There should be an interface that is interpretable to the doctor, and doctor should communicate with the agent in order to make the decisions or in order to change or modify the decision making process and all. So therefore, equally important is also the explanation interface, which often we call it human computer interface. So there are many prototype implementations has been done. There has been language evolved, that how we can write something very succinctly in a language and completely to explain something, give a query and can get an results. And primarily, there are explanatory machine learning also applied in psychological domains, and it often helps or dictates the psychological theory of explanation as the machine thinks and or machine do. And here I would also like to predict that this particular thing has also guided certain new research arenas. Now, since machine has been deployed widely in many practical scenarios, they are predicting the law outcomes in a court. They are predicting the medical outcomes, and also they should be fair, they should be unbiased. So all these, so nowadays you will see that Google has many of the translators in Google is a little bit biased towards the activity that is done by men and the activity that is done by women. So there has been research going on why this bias is from. Is it from the training data sampling bias, or is it from the model generation that has an inherent bias in it? And how can we change it? And also, this bias often governs our societal standings right now. I mean, if the gender bias, you can see that there is a paper. Yeah.
Sir, the model bias generally comes from the training data, right? So
generally,
if the training data is unbiased, then model can be biased. That's my question.
Yeah, it's a learning, right? So there should be some gaps. It is not a perfect algorithm that you are fitting in the model, right? Yes. So somewhere you need to fit your line for prediction. It's a plus or a minus in between, right? So it is not always the case. If you fit it perfectly in between, then edge points which you may not see in your training may create a bias.
Okay.
You're getting it? See, there are some boys, there are some girls. I fit a line in between. I separate it exactly. But suppose I use support vector machines. So I get a great margin and I separate. But I do not know the points that fall just near to my margin.
Yes.
right? So then models infer a bias, though my data do not have a bias,
Okay.
right? So all this you can see that whenever we see that Google has published a paper, Google AI, that it is more in India, it is more prone that woman cooks. I mean, there has been a controversy on that, but it also gives us a societal standpoint of Indian psychology, right? So, so all these research are coming up. AI, using AI in a fair means with an unbiased way, can we use it or not? So these are ample opportunities to make it. And someday you see there could be companies or there could be entrepreneurship opportunities floating up in near future that autonomous vehicle, if they are deployed, some autonomous vehicle make an accident, whose fault is this? I mean, which code it will be handled? There is no code for machine. I mean, which tool it will handle the case? That and there has been cases in UK. I read about that they have a trial with the autonomous vehicle with a dummy pedestrian crossing, and there is a blockage. So you have 4 people inside the vehicle. So the pedestrian are all 70 plus age. So your speed is such, either you can take a turn and collide in the block, or you can run over the pedestrian. So what will be your decision in an autonomous vehicle? Would you cross over the 70-year aged people, or there are young 4 people inside the car? Would you get them towards the blockage and then you have an accident? Which way you will go? So these are all very critical decisions that machine has to make, because we human used to make these when we drive a car, right? There are many shortcomings of the machine come up when we just deploy a reinforcement agent into a car. Someday, some years earlier, there was an accident that a vehicle is in automatic cruise control mode. It is following a leading vehicle. So if the leading vehicle speed get less, it also lessens its speed. Everything is going okay. But the front leading vehicle was human driven. Suddenly, there was a truck which was stopped in between a busy road. Then the leading vehicle was in 100 km/h speed. It just reduced a bit because it's a manual driver. And then it suddenly takes a right turn. The following vehicle was in 100 speed. When the leading vehicle reduces and takes a right turn, it doesn't notice within that time period that it reduces and takes a right turn. Immediately in front of it was a barrier of that truck. It just collides. Okay, so see what happened is that its automatic cruise control was following the leading vehicle. Suddenly it switches not to follow it. Why it switches not to follow it, even though there is a truck? It cannot see the truck because of the leading vehicle. So all these decision makings, as human do, machine does it in a different way, because models fills up the parameters to take the decisions. But how can we explain? How can we make it fair? All these are new companies. As you see, the proliferations of new AI startups has come up due to this. There are small avenues where we need agents to do all these activities to aid learning into these activities. So finally, there are some papers which also talks about the prototype of this human computer interfaces and all. And just this is a summary of whatever we covered, that we need an XAI good model, explainable system, as well as an interface to do with it. And primarily, it is deployed in many data analytics platform where people in multimedia, in medical image analysis, try to recommend and try to form an explanation of it. And sometimes it is also applied in autonomy in workforces, where there are drones which can say that which region is more attack prone, which region is less attack prone, and accordingly guide your troops of soldiers to that region and all. So it need to explain. I mean, if you guide your soldiers to certain region and where there is a bombing, then the agent need to explain that why he had taken a decision to guide in a misguide some soldiers in a place. So this should be explainable. I hope there no more introduction is needed. That we are still yet not at the position where we should be in terms of machine learning explainability. So that's what the DARPA gives a perspective in 2016-17, and after that, enormous research has been going on, and it is still on. I am saying that it's totally an open field, because there is no such one good thing that can explain everything, or there is no ceiling point of it. So if you are interested, you can directly dig into this, because next 10 years it will be still hot. So with that, so this is what I would like to make you one of the current research trends. Now, let me just go back into the summary. So let me go back into my board mode once again. So if you see that what we covered in machine learning, it looks like this. It's complete jungle, right? Can you see this?
Yes,
Can
sir.
you see?
Yes, sir. Yes, sir.
It's a complete jungle, meaning that if two books you open up machine learning, and I just tried to have two books and generate a word cloud of it, you see it's totally different. Different books of machine learning tackle the problem in a different way. Even I tackled in this course, the way that I taught is of different type, maybe a culmination of different books, but it's of a different way. So even the crowdsourced terms are also different. You can see, I mean, two books doesn't relate it. There are certain fundamentals we need to know. It's a complete jungle. But and as per the broad roadmap, if you look from AI towards deep learning, you will see that Turing's dream in 1950 that machines can think get gradually shaped up by Minsky, not Minsky, that McCarthy and all in 1960s to 1990s. Then this AI get very much boom. Primarily the search, the heuristics, the logics came up, the planning techniques came up. All these factors make things more reasonable and which we call artificially intelligent. Then from 1975, that Minsky and Papert's paper of perceptron, it's on 1957, but 1975, some of the researchers, including Rumert and all, showed the flexibility of learning from experience, and which we have studied in terms of supervised mostly. There are some unsupervised and reinforcement learning, and in a stochastic sense, Bayesian models and all. And it was a boom till 2010 until neural networks took over. So then Ruhmart, LaCoon, Bengio, and Geoffrey Hinton had a set of works, even Sejdi and all, from 1990s to 20 star star. I made it. I mean, it's upon your hand now how far you can reach it. And you can see the proliferation of CNNs, RNNs, DNNs, GANs, deep fakes. What else we can do? We are just thinking. I mean, every new day you will see that something new is happening in this. So it's still so hot, but we still have to travel a lot in the explainable domain. But things we can do with it is enormous, have an enormous potential. So I try to list some of the terms here that we covered mostly. And I mean, if you look at a glance at any point randomly, you know something about it, right? I mean, just take 15 seconds and look at a glance anywhere. You know something about it, isn't it?
Yes, sir.
I mean, if you do not know something about some term, either I have not covered, but if I covered, you do not know, it's my failure, not yours. Do not get surprised. Anyway, I think you know something about it. So okay, let us summarize. I mean, we are at the final point of this course. Let us summarize that the path we traveled. So we can tell that three parts we can summarize. One, we can summarize that we covered a little bit of theory. We covered a little bit of techniques. I mean, not a little bit, a vast lot of techniques. We covered it. And there are certain paradigms that evolved in fitting those techniques into it. So let me start with the paradigms because it will be more sense. So one of the paradigms, you know, that supervised is the theme of our course. It is one of the most promising learning technology because most of the time we do supervised learning. Whichever stream you are in, whichever problems you are solving, if you get a supervised setup, then it's the best. And mostly you will get a supervised setup because you learn from experience, which are leveled. Then we have seen some unsupervised approaches as well. I mean, the clustering and all. And it is often used to discover something new, a disease which is corona, to discover something new, some category of virus traits which is of different, you do not know, you do not have any label. So this is kind of invention and this is kind of a discovery, you would say. The third we have seen, it's a reinforcement type. So this paradigm has led us to find out that we do not have immediate labels like supervised, and it's better than unsupervised because some trainer is there. He just tells you that you do not go that way because it is not rewarding, but the reward you collect much later. And we have seen some setup, and primarily the control theory people, the electrical and electronics people may appreciate. In control domain, we apply it very much where there is a player who wants to play or an agent who wants to interact with the environment and take decisions. And also a little bit extension of this, we also have seen in terms of active learning somewhat, and sometimes we call it an online learning where a batch is given to you. Semi-supervised and all, I'm not putting it differently. It's just a variant between supervised and unsupervised. It fits somewhere in the middle. So these are the machine learning paradigms that we follow. And obviously, I just color it in a different color that neural is also a paradigm nowadays because it just invented or reinvented the deep learning aspect. So you can say that artificial neural networks, I would rather like to put it in terms of a technique, but you can say that it's a whole lot of a paradigm because it spawns a new branch. In terms of theory, we covered VC dimension, which is one of the key theory. And if you remember, it gives us the opportunity to think that learning is possible. Okay, I mean, it's a question of possibility versus probably we can learn. And VC dimension give rise that probably, approximately correct ways of learning. Then we also see something called a bias and variance, that how good we can search through and find our hypothesis, how much away that finding becomes with the true answer, right? That's the only trade-off between bias and variance we have learned. We covered very less about the complexity of your learning, which means that sometimes in k-means algorithms or clustering, sometimes we say that this algorithm is of this much complexity and computationally very heavy to run this. This is often a very interesting dimension in theory where the algorithmists or the theoricists try to invent new learning algorithms which can act in less computational overhead. So this is one of the thing. And the fourth thing is the Bayes theorem oriented or the Bayesian theory, which also I model it as a stochastic notion of theory, where we see that the graphical models, the Markov processes and all, and sometimes the naive Bayes algorithm stands over this Bayes theorem and all. So this is what primarily we covered in terms of theory, and these are our paradigms. Now, technique wise, I would like to just deviate it a little bit. I mean, you may not agree with me, but just I would like to say that we have something called a model, and we have something called methods. So for model, let me summarize it that you can easily understand there are linear models, linear regression, linear classifications and all. There are neural networks. This is a model, or rather artificial neural networks. There are SVM. This is a model that we give of our classification algorithm. We give nearest neighbors, KNNs. This could be our model. We give radial basis function, which could be a model of different types of learning we have seen. We give a Gaussian process, mixed models, all these things. We have graphical models like Bayes nets. We can say this is Bayes net and all. What else do we cover? I mean, obviously decision trees, concept learning, and it's just a Boolean formula. All these are models that we learn. What else? I mean, what else do we learn? Suggestions?
Bagging, boosting.
Here. That's why I call it methods, because see, bagging, boostings are culminations of this. One method we use, see, decision tree, I can use it using boosting. Ensembles, I will try to put it here. Okay, so let us try it here. If something is missed, I hope you know it's a jungle. It's a jungle out here of the methods. Now here I will just say that aggregation is one of the things that your friend was suggesting, that aggregation, which means the ensemble techniques we use. So we can ensemble two kinds of learning, weak learners into a strong learner. And in ensemble, as you can see, we use bagging, boosting, data boost, one of the things that you should know after a machine learning course. Then the techniques that we also used are regularization, right? It's a method, right? It can applied over any model to regularize. You could use validation. We know what cross validation, k-fold validation, stratified, and all these things. A little bit I covered sometimes. It's mostly covered in data mining and all this. It's input processing is also a method, because sometimes your input should be processed so that you get the relevant attributes to reason about. And this input processing is also included, which we covered, is called a transformation of the domains, right? That we covered. Sometimes we transform the X space into G space, right? Phi we transform from X to Z space and get a classification over the G space and then come back. Somewhat this is all about it, right? I mean, as far as I can remember in this course. So the way to go, I mean, let me summarize that what we can take home from here this course. One thing is, you can see we touched a little. I mean, those who are doing a deep learning course is okay, but those who do not do, you can think of an audit as well. You can also see in details the reinforcement learning course. There are courses in maths department, I guess, which is of stochastic process or something, and it sometimes covers some of the learning theory things that we cover. If you are more interested into theoretical side of it, there are course in computer science department which is advanced machine learning you can take. I think there will be a new course floated also, which is a stochastic or statistical machine learning, which also is a little bit of theory oriented statistical ML. So either this or this will be floated in alternative semesters, I guess. So this is one of the roadmaps that you could follow from whatever you have studied, and obviously the other thing is that it's very practical. So you go with the TensorFlows, PyTorch, all these libraries, and create your own functions, CNNs, TNNs, whatever neural network aggregations, ensembling, whatever you want, and can explore over new activities. As a research, as I pointed out, just to reiterate, one of the things that explainability, fairness, biasness is one terms of research that we usually look for. Explainability, fairness of AI technique, biasness of AI technique, ethics in AI technique. I forgot a course. There is a course in AI in ethics. In law department, there is a course AI and law, how the law making decisions are improvised by AI techniques. So there are courses AI and law. So all these new things that is of higher interest in machine learning paradigm. And as per the conferences and journal goes, the journal wise, JMLR, Journal of Machine Learning Research, is one of the best journals in this. You can also look at International Conference on Machine Learning to know about the papers. There is a conference, ICLR, International Conference for Learning Representation. These two are very premier conferences. There are journals like Pattern Recognition and Image Processing. We call it sometimes PAMI. Pattern Recognition and Machine Intelligence. And there are journals in computer vision like CVPR, the conference like CVPR, Computer Vision and Pattern Recognitions. And many more. I mean, there are Journal of Neural Networks, and there are many more. I mean, these are one of the pioneer journals and conferences where people used to publish, or good people used to publish. As per the theory, the VC dimensions and all these things has been contributed from Leslie Valiant, which is a Turing awardee. And he get the Turing paper. I mean, these are the names who got the Turing awards due to this. He got the Turing paper because of he proved that learning is feasible. And then followed by Vapnik Charbonenko with their statistical methods to all this. Actually, Leslie Valiant did this one. He proved that I can learn probably, approximately correct. So that's what Leslie Valiant is all about. And you know, with the proliferations of deep neural networks, the three musketeers that have received the Turing Award in the last 2 years: Yoshua Bengio, Geoffrey Hinton, and Yann LeCun. So you can see that this person has received in 2002-3 sometime. They have received in 2018-19. So you can see with this whole span, and in AI, there are many researchers who received Turing Awards, starting from the heuristics causality Julia Pearl to McCarthy, very early days. I mean, there are many people. So you can see still it is rich, still more things to contribute, more young minds, more young ideas to put into it. Look forward for you. And with that, let me conclude the course, and I would like to complete the circle with the same figure that I started off with, that don't get hooked into so-called the unrealistic world of things. Okay, machines are learning. Let us join hands. Thank you. That's all. Any questions?
Excuse me, sir. Sir, this is the slightly unrelated, but what is the main bottleneck in advances in AI nowadays? Is it the software algorithms side or the processing power available to us?
Okay, so processing power is one of the bottleneck, as you have underlined. So in many cases, what happens? The curated data we sometimes do not get. See, in practical cases, like as I give an example of medical imaging identification, you need doctors to curate, right? If you have a radiologist, then only he or she can tell that this particular image resembles that there is a cancer. So there is not a lot of data of it, and without data, your machine learning will not never be successful. That is one of the bottleneck in some realistic applications we have. For example, say suppose you try to get an autopilot, build a good autopilot for airplanes which will prevent crashing. Now, how many crash data you have? You have very less airplane crash data. That will prevent you some of the cases. That's why these GAN models are very efficient, because they could now create data, synthetic data. On the contrary, as you have correctly raised, there is a computational power limit. Though NVIDIA's and all the other companies are building newer GPUs, but all these operations, since we need to train backpropagate in a deep neural network, mostly which is the de facto model we use, you can see the number of iterations we need to make to finally converge as a stochastic gradient to get a minimum. And even if we multi-thread our operations, distribute in several GPUs, but still it is the computational resource is one of the bottlenecks. And the third bottleneck, as I in the initial part of my today's lecture I pointed, is still we are very short in explainability. We are hovering around, but there are a lot more scope of it, and we are still not satisfied with the explainability of machine learning.
Okay, sir. Thank you.
Any other questions? Okay, so Rohit, I can see you. Rohit and Ram will make scribes of today. I am sorry that preferably by Saturday, if I could get, since the grading deadline is coming, that's why. Okay, so if there are no more questions, we can stop recording and all. Good.